This is mathheals.com, where you can go to find more links to math YouTube videos. Let's take a look at simplifying radical expressions using properties of radicals. And first thing we're going to talk about is the product property. And we'll have various properties. Now this one, there's different versions of this, different ways you can write it. But basically, if you're yeah, B's probably okay, but let me choose different. I'll put P there. If you're multiplying two radicals together, and the indexes are the same, the number in this slot right here, then you can put them underneath a single radical like that. You can also go the other direction. If you have this, you can split it but into two separate radicals. Excuse me. So this first problem here, we have the cube root of -2 times the cube root of 13. It says use the product property to multiply, assume all variables can be any real numbers. Since the indexes are the same, we can multiply these together and put them underneath a single radical. So I got -2 times 13, which gives us a -26. Now remember, whenever you have a negative inside of a radical with an odd index, you can take that negative and bring it on the outside. So this gives us negative cube root of 26. Let's take a look at our next one. We've got the fifth root of -12 x to the fourth over 3 times the fifth root of 3 over 4x squared. Now we're multiplying these together, so I'll put them underneath a single radical with fifth root. So I got -12 x to the fourth over 3 times 3 over 4x squared. Now we can do some simplifying here. These 3 is going to cancel. And let me write it down again before I do any more simplifying. And I got -12 x to the fourth over 4x squared. Well, we've got -12 here, we got 4 here, they're both divisible by 4. 4 divided by 4 is 1. -12 divided by 4 is -3. So we've got the fifth root of -3 x to the fourth over x squared. Now remember, if you have x to a power over x to a power, you subtract a smaller exponent from a larger one. 4 minus 2 gives us 2, and we put x to that power where the larger one was, which was on top. When I say larger, I'm talking about the exponent. So we got -3 x squared over 1. So again, subtract a smaller exponent from the larger one. 4 minus 2 is 2, and we have x to that power where the larger exponent was, which was on top. Which gives us the fifth root of -3x squared. Now remember, whenever our index is odd and we have a negative number inside, we can take that negative and put it on the outside of the radical. So we got negative fifth root of 3x squared. And that's our answer. Now this next one is a little bit different. Remember how I said there's different ways you can work the product property? It says simplify each radical using the product property. Assume all variables can be any real numbers. Well, 48 is 2 times 2 times 2, 2, 4, 8, 16, 48. So 2, 4, 8, 16, 48. Okay. Now our index is 2. There is no number in this little slot right here, so it's by default 2, square root, which means we're looking for pairs of something. Here's a pair of 2's, and here's a pair of 2's. So a pair of 2's is going to come out, and this pair of 2 is going to come out. Now when they come out with multiplication in between them. So it's 2 times 2, and then we got a 3 inside. And 2 times 2 is 4, so our answer is 4 square root of 3. Now, why is this the product property? Well, I could split this up. I could split this up as the square root of 4 times square root of 4 times square root of 3. And then square root of 4 is 2, square root of 4 is 2, and then the square root of 3. We never show those steps, but that's implied when we're doing this. Okay, let's look at the 4th root of 80. 80, that's 2, 4, 8, times 10, so 2 times 5. 2, 4, 8, 16, okay, that'd be right. Now our index is 4, which means looking for a set of 4 of something. Well, here's 4 2's, so those 4 2's are going to come out in front as a single 2. So we got 2, 4th root of 5. And that's our answer. Here we got square root of 18a to the 4th. Now, up to now, these examples, nothing's come out of the radical there except for a negative. Nothing here but negative. Here's a 2, here's a 4. This one we're going to bring something out. And we'll talk more about that. 18 is 2 times 3 times 3. Now a to the 4th. We'll come back to that. First, let's look at the numbers. Here's a pair of 3's, so those are going to come out as a single 3. Okay, now the a's. What you do is you take your power, which is 4, you divide by your index. Index is this number in a slot, and if it's a square root, it's by default 2. So 4 divided by 2 is 2 with a remainder of 0. This is old style division. Now this first part here tells us how many a's come out. And this tells us how many a's stay in. So that tells us we're going to have 2 a's come out. And 0 a's stay inside. Well, the 3's are gone, the a's are all gone, so we got just a 2 in here. Now, it says, assume that all variables can be any real number. That means that this can be positive, can be negative. Well, you can never have a negative number come out of square root or any radical with an even index. Now, odd index is fine. Like up here, we had a negative number come out just fine. But when your index is even, you can't have a negative number come out. Well, how we ensure that it's positive is whatever variable comes out, you put absolute value bars around it. Like that. Now, in this particular case, the a squared, well, when you square something, it's always positive, isn't it? Negative 2 squared is positive 4. 2 squared is positive 4. So those absolute value bars aren't necessary here. So we've got 3a squared square root of 2. But again, anytime your index is even and you're bringing out a variable, you have to think of the absolute value bars. Let's look at number 6. We've got the cube root of negative 52 p to the 6. Okay, let's look at the number. Well, first off, we got a negative, and we got an odd index. Remember, if you have a negative and you have an odd index, you can go ahead and bring that negative out in front. So, I'm not even going to worry about that negative. Just put it out in front. 52 is 2 times 26, which is 2 times 13. Okay. Times p to the 6. Well, our index is 3. I'm looking for a set of 3 of something. And I don't see any 3 of any numbers here, so we can't do anything there but the p's. We're going to take our power, which is 6, divide by our index. So 6 here, divide by 3. That gives us 2 with a remainder of 0. This is how many come out. and this is how many stay in. So we got the negative out in front, and we're going to have 2p's come out, and we're going to have 0p stay in. And then 2 times 2 times 13 gives us 52. And that's our answer. Now notice I didn't try to put absolute value bars around here. The only time you have to worry about the absolute value bars is when your index is even, and not when it's odd. Let me start a new page. And let's look at our next problem. There's a lot of these problems. So we've got square root of 50 m squared into the third. Instructions still the same. Variables, or assume that all variables contain real numbers. Okay. First, let's look at the numbers. 50. That's 2 times 25, so 2 times 5 times 5. M squared into the third. Okay. So with our numbers, this is a square root. It's by default 2 for the index. So we're looking for a pair of somethings. Here's a pair of 5s. Those are going to come out as a single 5. Now our m's. Let's figure out how many m's we're going to have come out. We're going to take our power, so which is 2, divide by our index. It's a square root, so it's by default 2. So we're going to get 2 divided by 2 is 1 with a remainder of 0. So this is how many come out, and this is how many stay in. So we're going to have 1 m come out. 0 m stay in. Now n's. We got third power there. So we'll take 3, divide by our index. Index for square root again is 2. So we get 1 with a remainder of 1. This is how many n's come out, and this is how many stay in. So we're going to have 1 n come out. Now number-wise, we still have that 2 in there. We have 0 m's, and we have 1 n. So we'd have that. Now, we cannot have a negative number come out of a radical with an even index. So again, we have to put absolute value bars around the mn. That'll ensure that whatever comes out is positive. And that's our answer. Number 8. We've got the square root of x to the 13th. Well, for our x's, take our power, which is 13, divide by our index. It's a square root, so it's by default 2. So that gives us 6 with a remainder of 1. This is how many come out. So we're going to have 6 x's come out. And this is how many x's stay in. So we're going to have 1 x stay in. So we're going to have 6 x's come out, and we'll have 1 stay in. Like that. Now again, we brought out a variable. You have to worry about the absolute value bars whenever you bring out a variable from a radical with an even index. So we're going to put the absolute value bars here. But think what x to the 6 does. Well, actually, when you have x to any even power, it'll always become positive. So those absolute value bars aren't necessary, so we'll go ahead and drop them. And this is our answer right here. You get a drink. Okay. Second and next one. Got the index is 7, x to the 23rd. Well, again, we'll take our power, which is 23, divide by our index, which is 7. That gives us 3 with a remainder of 2. This is how many x's come out. This is how many x's stay in. So we're going to have 3 x's come out, and we'll have 2 x's stay in. Now, do we need to worry about the absolute value bars? No, because the index is odd. The only time you have to worry about the absolute value bars is when the index is even. So that's our answer. Okay, let's look at this one. Got the 5th root of a plus b to 27th power. Doesn't matter what we're talking about. Here we're talking about a plus b's. So we're going to take our power, which is 27, divide by our index, which is 5. That gives us 5 with a remainder of 2. So this is how many come out, and this is how many stay in. So we're going to have 5a plus b's come out, and we'll have 2a plus b stay in. Now our index is odd, so we don't need to worry about the absolute value bars. And that's our answer. This one's kind of a specific type, and we'll talk more about it after we work one. No matter where you are in math, if you can simplify your radicals, you should. Square root of 24 I can simplify. So I got 4 minus 24 is 2, 4, 8 times 3. So that's prime factorization. Now, with this is a square root, so our index is 2, so we're looking for a pair of somethings. Here's a pair of 2's, so that's going to come out in front as a single 2. So we got 4 minus 2, and then we're left with 2 times 3 inside, which is 6. We can only bring something out if it's a pair, like a pair of 2's, pair of 3's. Now, this type of form you see right here, you see this a lot in the quadratic formula, which we'll see later in this course, and then you see it in college algebra too. And basically, it says if you can divide this number and this number and this number by the same number, do so. Well, those are all divisible by 2. So 4 divided by 2 is 2 minus 1 square root of 6 over 2. Which gives us 2 minus square root of 6 over 2. And that's our answer. Let's look at another one of those. 12 minus square root of 48 over 24. Again, no matter where you are in math, you should simplify your radicals before you go on. 48 is 2 times 2, 2, 4, 8, 16, 48. 2, 4, 8, 16, yeah, 48. Okay, we're looking for a pair of somethings. Now here's a pair of 2's, those are going to come out. Here's another pair of 2's, those are going to come out. Now when they come out with multiplication between them. So I'll have 2 times 2 in front of the square root, and then a 3 over 24. 12 minus 2 times 2 is 4. Again, they should call this the 3-number rule or something. But if you can divide this number, and this number by the same number, do so. And those are all divisible by 4. 12 divided by 4 is 3 minus 1 square root of 3 over 6. Which gives us 3 minus square root of 3 over 6. And that's our answer. And this one, I got square root of 5 times square root of 20. Again, we're back to the product rule here. It says multiply and simplify. Assume that all variables are greater than or equal to 0. Assume that all variables are greater than or equal to 0. What they're telling you there is it's all variables are positive. So we don't need to worry about absolute value bars in any problem where we bring out a variable. Okay. So multiplying these two together, as long as the indexes are the same, you can put them underneath the same radical multiplied together. Now you don't want to actually multiply them together though. The reason why is you want to see what can simplify. 20 is 5 times 2 times 2. That's prime factorization of 20. Now after I do that, this 5 just carried down, and then this 20 is the 5 times 2 times 2. Remember the square root, we're looking for pairs of something. Here's a pair of 5s, those are going to come out as a single 5. Here's a pair of 2s, those are going to come out as a single 2. Now again, when they come out with multiplication between them. And there's nothing left inside the square root, so we drop it. So 5 times 2 gives us 10. Let's start a new page. And let's look at the next problem. We've got square root 3x squared times the square root of 6x. And again, it says assume all variables are greater than or equal to 0. So anything that comes out, we don't have to worry about the absolute value bars. Well, The indexes are the same. We're multiplying these together, so we'll multiply what's underneath them. And I'll put the numbers together. So I got 3 times 6. And I'll put the x's together. So x squared times x. Well, 6 is 3 times 2. And x squared times x gives us x to the third. Now remember, we're looking for a pair of somethings. Here's a pair of 3's. Those are going to come out in front of a single 3. Now the x to the third. Let's talk about the x's. Again, we'll take our power, which is 3, and you divide by your index. And this is a square root, so again it's 2. And this is old style division. 3 divided by 2 is 1 with remainder of 1. This is how many x's come out. This is how many stay in. So we're going to have 1x come out, and we're left with the 2 inside, and we said there's 1x left inside. Now normally I'd have to worry about the absolute value bars on that. But this says assume that all variables are greater than or equal to 0. So we don't need to worry about that, and that's our answer. Let's scroll down here. Now here we got -2 square root of 10 p squared q to the 5th times 5 square root of 8 p q squared. Okay. Now if you're multiplying radicals together, you multiply what's underneath them, assuming the indexes are the same. If you have numbers out in front, you multiply those numbers together. So -2 times 5 gives us -10. And we'll multiply these together, and I'll put the numbers together. So I got 10 times 8. I'm going to put the p's together. So I got p squared, p, and I'll put the q's together. So I got q to the 5th, q squared. Okay. I want to do the prime factorization. 10 is 5 times 2. 8 is 2 times 2 times 2. P squared times p gives us p to the third. Q to the 5th times q squared gives us q to the 7th. Now this is a square root, so we're looking for a pair of somethings. Here's a pair of 2's, that's going to come out. And here's a pair of 2's, that's going to come out. Now when they come out as the first pair of 2's comes out as a single 2. Second one comes out as a single 2, and they're multiplied by what's already out in front. Now for the p's. My power is 3. Divide by my index. It's a square root, so it's by default 2. 3 divided by 2 gives us 1 with remainder of 1. So this is how many p's come out, and this is how many p's stay in. Now for our q's. Take our power, which is 7. Divide by our index, which is still 2. So we get 3 with remainder of 1. And again, this is how many come out, and this is how many stay in. Okay, so we're going to have 1 p come out. We're going to have 3 q's come out. Okay, those 2's are gone. We're left with a 5 inside. We have 1 p left inside, and we have 1 q left inside. Now again, the instructions are assume that all variables are greater than or equal to 0, so we don't need to worry about absolute value bars. 2 times 2 is 4, times -10 is -40. pq to the third square root of 5pq. And that's our answer. Okay. We got some more properties. Now here, if you got the whatever your index might be, I would use I, but I's are kind of hard to see. If you got division, you got the radical of I don't remember what variables I used. I think they were m and n. So you got the radical of m over n. Then you can split it up. You put a radical around top, and you can put a radical around the bottom. Now your index stays the same. That doesn't change. You can just split them up. Now you can go this direction or you can go that direction. So that's when we're talking about division. And for simplifying radicals, in terms of fractions. So simplifying radicals in terms of fractions. First thing is no fractions inside of a radical. So no fractions inside of a radical. And second thing is no radicals in the denominator. So no radicals in the denominator. So when we're working on problems, we want to keep that in mind. Nope, we got another multiplication. My eyes are getting off. Let's go ahead and do this one. And then we'll look at those properties. Okay, fifth root of 36 times a plus b to the fourth times the fifth root of 54 times a plus b to the 13th. Well, we're multiplying the two radicals together, so we'll put them into a single radical, fifth root, and we'll have 36 times 54. And we'll put the a plus b's together, so we've got a plus b to the fourth and a plus b to the 13th. Now 36. 2 times 18, 2 times 2, 4, 2, 4, 12, 36. 54. That's 2 times 3, well, 3, 9, 27, 54. Okay. I did prime factorization of 36 and prime factorization of 54. Now a plus b to the fourth times a plus b to the 13th, you add the exponents. So you got a plus b to the 17th. Okay, now we're looking for, our index is 5, so we're looking for a set of 5 of something. Well, we have 2 3s there and 3 3s here. So we got 5 3s total. So those are going to come out in front as a single 3. Now 2s I can't do anything with because there's only 3 of them. Now the a plus b's. Again, we take our power, which is 17, divide by our index, which is 5. And that gives us 3 with a remainder of 2. This is how many we have come out, and this is how many we have stay in. So we're going to have a plus b to the third power. And inside, we said we had the 2's remaining. 2 times 2 times 2 is 8. And we have 2a plus b's. So we got a plus b to the second power. And that's our answer. Okay, now let's look at division. We've got square root of 2/9. It says simplify each expression. Assume all variables are greater than 0. Assume that all variables are greater than 0. They're telling you don't worry about absolute value bars when you have variables. Well, we can't have a fraction inside of a square root. We can't have a fraction inside of a radical, we said. Our property says we can split this up. You can put a square root on top and square root on the bottom. Well, that doesn't seem to do us any good because we said we can't have a radical in the denominator. But in this case, square root of 9, 9 is 3 times 3. With the square root, we're looking for a pair of somethings. Here's a pair of 3s, so those are going to come out as a single 3. So our answer is square root of 2 over 3. Number 18. Get the cube root of negative 8a to the 33rd over 27b to the 15th. Well, we said we can't have a fraction inside of a radical, so that's the main problem here. Our property allows us to put a radical around top, so we've got the cube root of negative 8a to the 33rd, and then we can put a cube root around the bottom. And we've got 27b to the 15th. Now by breaking this up, we can focus on each piece separately, and that helps a little bit. Now up on top, our index is odd, and we got a negative number. Remember, we said we can just take negatives and bring them out of the radical, assuming your index is odd. Now 8 is 2 times 2 times, well, 3 2's. And then we got a to the 33rd. On the bottom, 27 is 3 3's, b to the 15th. Well, our index is 3, which means we're looking for a set of 3 of something. Here's 3 2's, so those are going to come out as a single 2. And down below we have 3 3's. So again, our index is 3. We're looking for a set of 3 of something. Those set of 3 3's can come out as a single 3. Let's look at our variables now, the a's. We'll take our power, which is 33, divide by our index, which is 3, the number in the slot here. That gives us 11 with a remainder of 0. This is how many come out, and this is how many stay in. So we're going to have 11 a's come out. Now in this one, the b's. We take 15, divide by 3, gives us 5 with a remainder of 0. So we're going to have 5 b's come out, and we'll have 0 b's remain in. So we're going to have 5 b's come out, and there's no b's left inside, so actually our radicals both disappear. Now in this case, by using that property, it allowed us to break them into smaller pieces so we could work each one and have it a little bit easier than this whole mess right here. Over here, it allowed us to, even though we couldn't simplify the top part, it allowed us to get rid of the fraction inside of a radical by doing that. Let me start a new page. And let's take a look at this one. Got the cube root of 128 over the cube root of 2. Well, the main problem here is we can't have a radical in the denominator. Now, there's nothing I can really simplify. The top part I can simplify a little bit, but we could merge this back into a single radical, putting a fraction together. So 128 over 2. You can go both directions on your formula. Why would we do that? Well, because I could see that 128 is divisible by 2. So this becomes the cube root of 64. If I did the prime factorization of 64, that's 2 times, well, 6 2's. 2, 4, 8, 16, 32, 64. Now our index is 3, which means we're looking for a set of 3 of something. Here's 3 2's. Those are going to come out as a single 2. And here's 3 2's. Those will come out as a single 2. Now when they come out with multiplication between them. Now there's nothing left inside of our radical, so it disappears, and 2 times 2 gives us 4. Let's take a look at this one. Got square root of 225, m to the 9th, n to the 4th, over square root of 5m n to the 6th. Now sometimes, of course, the main problem is here we can't have a radical in the denominator. But sometimes you can see that if you have a radical on top and radical on the bottom, that if you merge them together, they would simplify a little bit. And that's what this looks like. So let's go ahead and temporarily put them together. Sometimes you temporarily put them together, you simplify, and then you break them back apart. As weird as that seems. Okay, I put them together. I got 225 divided by 5. I have no clue what that is, but let me see. That's 45. Is that right? 5, 2, yeah, 45. Now here we have m to a power over m to a power. And this is like the first power. If I were to put an exponent there, it would be a 1. Remember, if you have m to a power over m to a power, you subtract a smaller exponent from a larger one. 9 minus 1 gives you 8. And you're going to have m to the 8th where our larger exponent was, which was on top. Now the n's. I got n to the 4th over n to the 6th. I'm going to subtract a smaller exponent from a larger one. 6 minus 4 gives you 2, and you're going to have n squared where the larger exponent was, which was downstairs. So we're putting it in the denominator. Okay, that's as much simplifying as we can do, so let's split them back apart. So we're going to put the square root on top, and we'll put a square root on the bottom. On the top part, I'm going to write that number, the prime factorization, that number. That's 3 times 3 times 5, m to the 8th, over square root of n squared. Now our answers say assume that all variables greater than 0, so we still don't need to worry about absolute value bars. So let's look at the m's. Take my power, which is 8, divide by my index. It's a square root, so it's default 2. So that gives us 4 with a remainder of 0. This is how many m's come out. We're going to have 4 m's come out, and this is how many stay in. So we're going to have 0 stay in. Now, this is a square root, so we're looking for a pair of numbers, or pair of somethings. Here's a pair of 3's, so those are going to come out as a single 3. And we said we have 4 m's come out. We're left with a 5 inside, like that. Excuse me. Now the n's. Our power is 2. Divide by our index, which is 2. That gives us 1 with a remainder of 0. This is how many come out. So we have 1 n come out. And this is how many stay in. So we have 0 n stay in. So we have 1 n come out. And that's our answer. Let's take a look at one more of those. So we've got square root of 144, a to the 10th, b to the negative 2, over square root of 6, a to the negative 12, b to the 6. Now I notice that this has a, this has a, this has b, this has b. These look like maybe they would simplify a little bit. I'm not sure how much. So it looks like it'd benefit us to put it into a single radical. So put a square root, and I put the fraction together. Now if you remember from before, when we have a negative exponent, we want to take it opposite of where it's at in the fraction. So this b to the negative 2, we want to take it down to the denominator, and it'll become b to the positive 2. This a to the negative 12, I want to take it up on top, and it's going to become a to the positive 12. Anytime you move anything opposite of where it's at in a fraction, the sign of the exponent changes. So I already have an a to the 10th up here. I move the a to the negative 12 up on top, and becomes a to the positive 12. Now this one already had a b to the 6. I take b to the negative 2 downstairs, and becomes b to the positive 2. Well, I can simplify those a little bit. A to the 10th times a to the 12th is a to the 22nd. B to the 6 times b to the 6 times b squared is b to the 8th. Well, the numbers I could do something with. 6 goes into that evenly, I think. 24. 144 divided by 6 is 24. And then a to the 22nd, b to the 8th. Okay, that's about as much simplifying as I can do with that fraction, so let's split it back apart. We only put it in there temporarily so we can simplify it a little bit. And this right here definitely looks a lot easier than our initial problem. Okay, 24. That's 2 times 2, 2, 4, 8, 24. A to the 22nd. And then down here, b to the 8th. We're dealing with the square root, so we're looking for a pair of somethings. Here's a pair of 2's. That's going to come out in front as a single 2. Now for the a's. Take our power, which is 22, divide by our index. This is a square root, so it's by default 2. That gives us 11 with a remainder of 0. So this is how many a's come out. We got 11 a's coming out and 0 a's staying in. So we're going to have a to the 11th. The square root 2 times 3 is 6. That's staying inside. Down below are b's. Our power is 8. Divide by our index, which is 2. It's a square root. So that gives us 4 with a remainder of 0. So we're going to have 4 b's come out, and we'll have 0 stay in. So we've got b to the fourth. And our radical disappears since there's no b's left inside. And that's our answer. Let's look at these next problems. It's kind of a little bit weird. They're trying to really demonstrate when can you multiply radicals together is what they're trying to emphasize here. Let me grab a drink. Okay. We can't multiply these radicals together. The indexes are different. Whenever the indexes are different, you can't multiply them together. Well, let's write these in rational exponent form, fractional power. This becomes 5 to the 1/2 times 2 to the 1/3. Whatever number's in this little slot right here, that's called your index. Since there is no number here, it's by default 2. It's a square root, so we put a 2 here. And then we put a 1 up on top. Now in this one, this was the cube root. So the number in the little slot here, our index is 3. So that's why we put a 3 in the denominator. And then it's by default 1. Now think what I've just said. The index is what goes in your denominator. So the index is what goes in your denominator. If the indexes are the same, we could multiply these together. So all we have to do is get these indexes the same. So I need to rewrite them with the same number. This is 2 and this is 3. Basically, we want to get a common denominator, which would be 6. Now here I multiply this bottom part by 3, so we multiply the top part by 3. So we got 5 to the 3, 6, times, here I multiply the bottom part by 2, so multiply the top part by 2. Like that. Well, now the denominators are the same, and denominator is your index, so we can put this back into radical form. And the 6 would go here, and then we'd have 5 to the 3rd times 6 goes here, and then 2 squared. Again, how it works is whatever is in your denominator is your index. Goes in the slot there. Whatever number's on top is your power that you can put inside. Well, now these both have the same indexes, so we can multiply them together. So we got 5 to the 3rd times 2 squared. Um, 5 to the 3rd, 5 times 5 is 25, times another 5 is 125. 2 squared is 4. So that gives us 6 root of something. 2801 not 500. Is that right? 250? Yeah, 500. So that'd be our answer. Let's look at this one. We've got square root of 10 times the cube root of 3. Now this is a square root, so it's by default our index is 2. This is a cube root, so by default our index is 3. I can't multiply these together because the indexes are different. Well, we can put it into rational exponent form, fractional power. So this one would be 10 to the 1/2 times 3 to the 1/3. Again, the index, whatever number is in the slot here, goes in your denominator. Whatever power is here is by default 1 if there is no power. It goes up on top. Here, the index is 3, so it goes in our denominator. The power is 1, so it goes up there. Again, for us to multiply these together, they have to have the same indexes. So we have to get the same denominator. So this one becomes 10 to the 3, 6. And this one becomes 3 to the 2, 6. Here I multiply top and bottom by 3. Here I multiply top and bottom by 2. Well, now they have the same denominator, so I'll put them back into radical form. So this would be 6, and that'd be 10 to the 3rd. And this one would be 6, and this would be 3 squared. see what that gives us. 6, 10 to the third times 3 squared. And I'm trying to think if this works out nice in any sense at all. I don't think it does. So 10 to the third is 1,000. 3 squared is 9. So that gives us 9,000. Like that. Sometimes in these problems, after you merge them together like that, you may have something that looks like this. Like 6 here, and then you have 5 to the third, and 2 to the ninth, or something like that. We got a property that says if you can divide this number, and this number, has to be all your index and all of your powers inside, all of them, by the same number, do so. Well, these are all divisible by 3. 6 divided by 3 is 2. 3 divided by 3 is 1. 9 divided by 3 is 3. Which then just gives us the square root of 5 times 2 to the third, like that. Which would give us 2 to the third is 8 times, that's 40. And actually that simplifies, doesn't it, now that I'm saying that. That'd be 2, 4, 8, 40. Looking for a pair of 2's. Here's a pair of 2's, so that comes out. And our answer would be 2 square root of 10. Now, that's what I was looking for up here. But I was looking at my index, which is 6, 3, and 2, and those aren't, there's nothing that divides into all of those. Now, if I just chose 6 and 3, I could, but again, it has to be everything going across here. And I think that's the last problem. Yes, it is. So let me stop the recorder and save this.